Good afternoon, everybody. We are in the middle of a summer school in medical physics here at IFUNAM that began the last Monday, June 12th. That will be done tomorrow, Friday 16th. And for who just came today for this colloquium, I want to tell you we are celebrating 20 years from the first admission of the medical physics program at IFUNAM. And we here today, we have the colloquium of the Physics Institute of IFUNAM will be given by one of our invited professors from Queen's University in Belfast. And we know now they are watching us directly from the UK. I will present you Dr. Lorenzo Stella. Dr. Lorenzo Stella is professor at Queen's University in Belfast, Northern Ireland in the UK. He has a PhD in the theory of condensed matter at the International School for Advanced Studies in Italy. He did his postdoc at the Universidad del País Vasco in Spain, San Sebastián, and he was a research associate at the King's College of London in England. Dr. Stella worked in as applied he did his thesis in the application of statistical mechanics to hard combinatorial problems. And he applied and developed several numerical approaches, including classical and quantum Monte Carlo techniques, non-adiabatic molecular dynamic, time-dependent density functional theory, plasmonic, and out of equilibrium molecular dynamics by means of generalized Langevin equation. So today, he will speak about the Perovskite nanoparticles for magnetic hyperthermia, an approach, a theoretical and experimental approach. Welcome, Dr. Stella.
Thank you. Can you hear me in the back? Yes. Thanks, Gerda. Thanks for the invitations. I want to thank also the Institute of Physics and the IFUNAM for giving me this opportunity to tell you something different, in fact, something new that we have been doing at Queen's University Belfast, along with several colleagues. And just because I don't want to forget to acknowledge all this contribution, let me start with the acknowledgement. First of all, the PhD students working with me, James Cook, he is behind all the coding and the simulation, so he is very good coder. And along with me, he worked on the modeling of the magnetic hyperthermia. You have more about this in a few minutes. My experimental colleagues are, the direction of the experimental part is from Danai Pulide in the School of Chemistry and Chemical Engineering, and the direction of characterization of the magnetic properties, Solveig Fenton in the School of Mathematics and Physics, which is also my school. And all the experimental and most of the characterization has been done by another very good PhD student that we have at Queen's University, Catherine McBride, and she's going probably to defend this year or the next. So let me give you a little outline of the talk as I prepare. First of all, I want to introduce a few important properties of magnetic nanoparticles and a property of very small magnetic nanoparticles, which is superparamagnetism. Then I'll introduce the magnetic heating, the property of some magnetic nanoparticles to heat up, a certain large temperature in solution and hyperthermia. There are several materials used to, using these magnetic nanoparticles. Possibly the most common is iron oxide, ferrites. We focus our attention on manganites, in particular this lanthanum strontium manganese oxide, in brief LSMO. I'll show you some experimental curves obtained at Queen's University, and I comment about some properties and also how hard it is to extract the heating power of these magnetic nanoparticles. Then I introduce the part that I love the most, the computational part, and the main equation of this game, which is the stochastic Landau-Lifshitz-Gilbert equation, or again in brief SLLG. This is the equation we use to model the heating of magnetic nanoparticles. And finally, I'll show you some results, some numerical results that we recently obtained about the magnetic susceptibility of these magnetic nanoparticles in solutions, and how from this information we extract the specific absorption rate, which is a way to quantify the heating power of these magnetic nanoparticles. So let me start first with magnetic nanoparticles. Those can be thought, at least with a certain simplification, as tiny magnets, tiny bar magnets that you can find in solutions. How small are these magnets? Well, usually the nanoworlds is, the boundary of nanoworlds is about 100 nanometers. In fact, it turns out that our nanoparticles are on the verge of the nanoworld. They are about 100, 150 nanometers, so they are large nanoparticles. And here you can see a SEM image from Catherine's paper. One of the most important property of magnetic nanoparticles, the small one, is that they are single domain magnets, ferromagnets. What does it mean? Usual magnets, they are made of several domains with different magnetizations. Single domain nanoparticles are actually made of a single domain, and we can associate one vector, the magnetization density, to the whole of a nanoparticle. Why is this important? Well, this gives a very determined response of a nanoparticle to the, for instance, an external magnetic field or an internal one, as we see later. What happens if the experimenter apply an external magnetic field, perhaps an alternating external magnetic field? There are two way of the nanoparticles to respond. First of all, it can coherent reverse the magnetizations, so the entire domain reorient or rotates in order to align as much as possible with the external magnetic field. This is called coherent magnetic rotation, or Néel rotation, after the French physicist Néel. But there is also another property, and this is very important if the nanoparticles are in solutions, because those are rigid bodies, and so they can rotate as a rigid body. So this is a rigid body rotation in water, and this is called Brown rotation, from another scientist, Fuller Brown. Now, this is normal. We can think as very tiny magnets, but there is a rather peculiar property which manifests, in fact, for very small nanoparticles, which is called superparamagnetism. Now, we can think of the magnets, the orientation of the magnets, as the orientation which minimizes some energy. And in fact, there are two possible directions without external fields that minimize this energy. And here is the depiction. So there are two valleys. Let's say, just to fix the attention, that's one direction which minimizes the magnetic energy is this arrow to the left, and the other valley as the arrow on the right. And without external field, they are absolutely the same. Now, the height of this barrier depends mostly on two parameters. One is the magnetic anisotropy, which I think for this particle is 10 to the 4 ergs per centimeter cube, if I'm not wrong. And the volume of a nanoparticle. So the larger the nanoparticle, the larger is this barrier. So what does it mean? It means that if I have a large nanoparticles, there will no thermally activated spontaneous jumps from one valley, from one orientation to the other. However, if our nanoparticles is very small, as an effect of the thermal agitations, the internal magnetization density can invert randomly. And this random magnetic inversion at higher enough temperature is called superparamagnetism. Of course, if we apply an external magnetic field, even the superparamagnetic particles will try to align, but still will have some fluctuation. This is a properties of the nanoparticles. It's not a property shared by, let's say, larger ferromagnets. Why is this important? Because all these properties of the nanoparticles, all this way to respond to an external field, they contribute to the heating of a nanoparticle. So to the dissipation of some external source of energy. The external source of energy that we commonly use is an alternating external magnetic field, which is usually done either with a coil. We usually have a coil in the laboratory in Queen's University. Other laboratory they have a ferromagnetic core. So we have our nanoparticles that have been synthesized in a way that I'm going to tell you in 1 second. They put in a little vial. The vial is placed here in the coil, and some current is some alternative AC current is passing in the coil, and then there is as a response of this an alternating magnetic field. What is the frequency of this alternating magnetic field is in the radio frequency range, so RF, 50 kilohertz roughly to 1 megahertz. And usually we don't want too large amplitude of this external magnetic field. There are several values just to fix the attention again, say 10 kiloampere per turn in SI units, in CGS EMU units this is 125 Ørsted. What happened? This is what they do, not personally what I do. Well, they say those are the parameters for the experiments that has been performed at the School of Chemistry and Chemical Engineering in Belfast. Here you have a timeline, I think up to 40 minutes, yes, of exposure to the alternating magnetic fields. And this is the temperature. There are many curves, just focus on the temperature. We start from room temperature, and here is as high as 60 degrees. There is a little thermometer in the vial. I'm kind of simplifying the experimental setup. And if I fix attention, those are several compounds. I explain in 1 second. You see that all of them, they start from room temperature and they rise the temperature of water up to a certain temperature. And this is the typical heat curve that we can test in the laboratory. And of course the heating depends on the kind of magnetic nanoparticles. In fact, in our case we use manganides, lanthanum strontium manganides. So the heating power depends on the dopant, on the doping, and also on the way these nanoparticles are synthesized. And I'll go through all these points. What is the goal of the experiments? Try to control the heating, to predict the heating curve, starting from the magnetic properties, and to engineer the magnetic properties to target a certain windows. What is the goal of the simulators like me, of the computational physicists, is to understand the microscopic model which is behind the heating of nanoparticles. But there is, okay, the question is, of course, why these nanoparticles heat up, and then I use what I previously explained. There are two types of mechanism. The first one is the viscous friction, so the particles, I said, they rotate like rigid bodies. There is the liquid is used as viscous liquid like water, and so some energy is dissipated in this way as we dissipate energy as friction. The other way is dissipation through hysteresis losses. So there is this change, coherent change of magnetization driven by the external magnetic field, and this is due to the Nehel mechanism. So those are the two main mechanisms. Since we're using large enough nanoparticles, and we said that this mechanism is important, especially for superparamagnetic magnetic nanoparticles, I will neglect this mechanism in the rest of the talk. I explain our motivations, but there is a greater motivation, of course, and probably you all already know about this, which is a medical application of magnetic nanoparticles. And the idea is to deliver target hyperthermia using magnetic nanoparticles. Again, I'm going to provide a very simplified idea. I'm aware of all the difficulties, and probably you even more aware of what I am of the difficulty in delivering this cure. If one day we'll have this kind of hyperthermic cure, but the idea is relatively simple. So one hopefully can inject the rightly designed magnetic nanoparticles in the body. Hopefully these nanoparticles are functionalized so that can reach the region that we want them to reach, the malignant cells. Then we can switch on the source of alternating magnetic field, possibly not a huge coil, a more handy source of alternating magnetic field, heat up to a certain temperature, not hundreds of degrees, because we want to kill the malignant cells. We don't want to damage the remaining tissues, of course. Again, from the medical part of this research, the idea is the best treatment will be done in these mild hyperthermia windows, so from 41 to 46 centigrades, which is reachable with, by the way, our nanoparticles. When, and you're supposed to know when to stop this the radiation by radio frequency, we can stop also the action of the magnetic nanoparticles, so the heating, and then they will hopefully be, let me say, the body can get rid of them simply. They hopefully don't stay in the body. There are many uncertainties, probably many more on the medical side, but from the physical and engineering side, our main question is how to target the right windows of temperature. We are not the only one interested in this magnetic hyperthermia. It's been a rising field. I don't quite like to show these figures, but this show that there is a wide interest in several areas. In fact, it's a multidisciplinary interest. We have a more confined goal, and let's see what we can do to target this goal. So I said that there is a window that is the window of mild hyperthermia that is possibly the most useful treatment. Let's see what is probably the main material used for magnetic heating, which is magnetite, just a ferrite. This is very good, it's biocompatible. There are being reported very large values of the specific absorption rate, so the heating power. It's not toxic, you said. There is just one issue. If you just leave your magnetic field on, these particles, they can heat up considerably. In fact, the only intrinsic mechanism to stop these magnetic nanoparticles to heat up is the Curie temperature. At a certain point, the magnetic nanoparticles, they are no longer ferromagnetic. It's the Curie transition, and they are not going to heat anymore. So they're very good at heating. It's difficult to control this heat. Is there any other candidate that we can use, or one can possibly use, that has a better controllability? Well, recently a lot of attention has been focused on this completely different class of materials. They're called manganides. One prototypical, possibly the most famous one, is this lanthanum-strontium manganese oxide. The parent compound is lanthanum manganese oxide, and this is doped with strontium. They form these perovskite structures. There are these octahedral, the blue or light blue atoms are oxygens. In the middle we have manganese, and then in the so-called A side we have lanthanum in the parent compound, and we can dope these A sides with strontium, for instance. What is the advantage of using this LSMO? That the Curie temperature is much lower. In fact, has been reported in some compounds to be 50 degrees Celsius. This is much better. So we can really have a self-limited hyperthermia using this, ideally, using this magnetic nanoparts. There are drawbacks, of course. Manganese is not something that you want to have in your body, but also all these nanoparticles are going to be coated in order to protect them, to avoid coagulations, and also to enhance the capability to target the tumor. So we want to have self-limited hyperthermia, and so we're going to investigate lanthanum strontium manganese oxide nanoparticles. As I said before, those are complex materials. The properties depends both on the dopant and the doping and the synthesis. Let's start with the dopant and the doping. This is the magnetization. Again, we use EMU units, CGM units. Magnetization as a function of the field applied, and those are 4,000 Ørsted, so those are 0.4 Tesla, I think. I hope you can see, so there are three compounds. This is lanthanum strontium manganese, this is doped with barium, and this is doped with calcium. As you can see, the saturation magnetization, the maximum magnetization that you can achieve, it depends on the doping, on the dopant, sorry. What also depends, and we're clearly interested into this value on the doping, is the Curie temperature. This time in Kelvin. So for instance, if I dope with calcium, you see that it will switch probably too early. Barium is okay at room temperature, but it's probably also switched too early. The LSMO, as I said, has a high enough Curie temperature. This is why then we focus the attention on the compound doped with strontium. So let's see the heating power. This again is usually measured in SAR, specific absorption rate, and I hope you can see is watts per grams of manganese. This is what you find in the articles. And this is part of the hard part of experiments. If you just measure with your thermometer vial purified water and no magnetic nanoparticles, there is a little increase of temperature. This is called the blank heating. This is due probably to either eddy currents in the liquids, most likely some dispersed infrared radiation. We measure this, of course, before every experiment, so let me say a positive heating is above the blank, a negative heating, if we can say this, is below the blank. And again, this is a small figure, unfortunately, but if you can see the lanthanum strontium manganese for different level of doping is always above the other compounds. And the doping with 0.35 amount of strontium seems to achieve the highest SAR. We wanted to understand a little bit better why, or what is peculiar in this compound, so the rest of this talk is mostly focused on this LSMO 35, which stands for 0.35 doping of strontium. Okay, life is much more complicated than that. Those magnetic nanoparticles were synthesized with the salt gel method, so there was a solution of the various oxide. Details that must be asked to the experimentalist. The solution form was sol, then the solvent is extracted, and there is a nanostructured gel. This is dried out, calcinated at high temperature, then grinded, and this gives the LSMO nanoparticles in the conventional way. And you can see the saturation magnetization, it's about 4,000 EMU per mole. Now, after a few attempts, found out the best technique, the best synthesis for these particles is to add during the salt gel process also exposure to microwave. So those are microwave. So it's a microwave salt gels synthesis. The shape is more or less the same, but if you look at the scale, now the saturation magnetization is about 20,000 EMU per mole. So roughly, well, almost 5 times large. What does it mean? It means that the crystallinity of our nanoparticles is also important. Initial nanoparticles probably were not that crystalline, and also the magnetic properties suffered of this lack of crystallinity. These microwave nanoparticles are much more pure, if you want, and also the magnetic moments is much larger. In fact, it's much close to the theoretical value, if I remember correctly. What about the SAR? Yeah, at the end, interested in the SAR. Here you can see a correlation of the SAR, so the heating power with respect to the susceptibility of the magnetic nanoparticles. Those are the conventionally salt gel synthesized nanoparticles. Those are LSMO 35 nanoparticles with 100 megawatts, I think, is it possible? So 100 minutes probably microwave exposure, 200 minutes and higher. And you see that there is a very nice correlation between, let me say, how much time has been exposed to microwaves and both the susceptibility and the SAR. The susceptibility also depends on the crystallinity of the sample. So at the end of this engineering that was done, in fact, in the School of Chemistry and Chemical Engineering, we have very good compounds, relatively close to the theoretical value for magnetizations, still pretty large, 150 nanometers, perhaps a little bit less in session on average. So we have something that we can start studying also from the numerical point of view. But first of all, we have to characterize in more details the heating curves so that we can match the macroscopic values that we get from the experiments to the microscopic values that we get from the simulations. And in particular, if you look at these, the highest curve, which is again LSMO 35 with microwaves, you see there is a very steep initial rise of the temperature and then something more gentle and saturation. What is this saturation due to? Well, the system is measured in so-called non-adiabatic conditions, so the vial is open, the vial is not isolated, so the heat eventually escapes to the environment. And so there is a balance between the heat provided by the magnetic mechanism and the heat lost to the environment. And this is why we have this saturation. We can also understand this shape, which is 1 minus an exponential. In fact, oops. Yep. Yep.
For instance, when you say 0, 0, 30, you mean 30 minutes or 30 seconds?
Those are 5 minutes, 10 minutes, 50 minutes, 60 minutes, 40 minutes. I think initially she also will go up to more than 1 hour, and so those are cut. Because the reason is that one can check the saturations when the value of the temperature saturates. It doesn't really matter if I go on for 1 hour or 2 hours. So those are just cut for 40 minutes. Thanks. So what I was saying, oh yes, this shape is 1 minus an exponential, can be understood as through the Newton laws of heating, so textbook physics if you want. In fact, we tried this analysis, we tried to fit everything with a single set of coefficients, and that was not possible. And it was not possible indeed because there is this quick heating, rising up of the temperature, and then something more gentle. So of course, if you're not able to fit with one set of parameters, you'll do with 2 sets. So this in the literature for magnetic heating is called the Box-Lucas equation. So we fit this heating curve with the initial temperature, then some set of parameters, the first one, A1 and B1, and then the second one, B2 and A2 and B2. A1 for the first bit, and then B2 for the second bit. The fits, you should probably not even see the black line because it's very good. How can we interpret this? Well, okay, we go to the experimental articles, and we see that after, processing of this quantity, we can associate to the first part of the slope a very, very high SAR, like almost 2,000 watts per grams of manganese. And probably, okay, I might have flashed this information before. We have 10 milligrams of nanoparticles per each milliliter of solution, if I remember correctly. While the second part of this Box-Lucas equation give us 44 watts per gram of manganese, so a much lower heating power. And this is part of somehow the confusion that there is in literature, because there are several ways to assess the SAR from the experiments. There are non-issue for each way. This is one of the best, in fact. Another way is just to measure the initial slope. This is the initial slope method. There is another famous method, which is the correct initial slope method, which is after Wildeboer. This is one of the most used. If you use, and they also provide you with, MATLAB script, an Excel spreadsheet. This is very useful. You put the heating curve there, and you find a very different value of the SAR. The reason for that is that in this method, it is assumed just one heat loss coefficient. And the heat loss coefficients here and there, they are very much different. So for curves that you can fit with just one of these box-Lucas equations, usually the two methods, they agree pretty well. But we are exploring something that's not been much explored so far. Most of the research is on fluorides. We know that the Curie temperature is low enough, so that might be a glimpse of phase transition. A glimpse of this change of magnetic properties due to the magnetization of your magnetic nanoparticles. Of course, here we have, those are 20 degrees above room temperature. Those are 50 degrees, is still lower than the Curie temperature of the magnetic nanoparticles, but what is measured is the temperature of water. The temperature of a nanoparticle most likely is way higher. So that might be a glimpse of phase transition. Before saying anything about this, we need to be sure about this large value, because it seems too large. And for that, we can use the modeling, and we want to use both analytic models, but also, let me say, numerical models. And I'll show you in brief, the main ones. So the microscopic question for the computational physicist is, what is the thermal response of a magnetic colloid, so magnetic nanoparticles in solution, to an alternating magnetic field? And the challenge in finding this answer are several. First of all, you usually don't have one magnetic nanoparticles, you have several of them. So the challenge of many body physics, dipole-dipole interaction, colloidal interactions. We usually want to use small magnetic fields, especially in view of medical applications, but in the lab you also might also want to characterize your particles since I'm magnetic field, and the challenge is to reproduce both linear and nonlinear response in strong magnetic field. Then, of course, this is probably the next stage, also to try to model the complex cellular environment. We might be able to model the heating of a single nanoparticle, but this is not in isolation, of course, not in vacuum. Especially in the cellular environments, they're much more than a solution, they're much more than blood. There will be interfaces, different tissues with different viscosity or permeability. Those also are challenges. And finally, there's also complex chemistry of magnetic nanoparticles. It's already known that, for instance, fluorides, they go to degrade in the body or in vivo. And also all these magnetic nanoparticles, they form what's called a corona of proteins, which is the answer of the body to a foreign particle. Now, for today, I just focus on one of this challenge, in fact, the dipole-dipole interaction of magnetic nanoparticles, and I will use linear response because our fields are pretty low. So, okay, for all the students who follow the school, this is kind of revision. I'm going to show similar slides. Apologies for that. Or not, maybe it's useful. So how can we model magnetic nanoparticles, or in general nanoparticles in solution? Well, of course, one can have the full simulation. I can have my magnetic nanoparticles, all the molecules of water. This is still too expensive. There are 3 coordinates and 3 components of the velocities for each of the guys in these pictures. There's too much information. So what we do, instead of using explicit solvent, we use implicit solvent. So a medium, a continuous medium, not formed by a molecule, with some relevant physical property. In this case, the relevant physical properties are the density, the viscosity, and of course the temperature of the medium. This, as in the case of a Brownian motion, we have to account for the, let me say, hidden granularity of the medium, the fact that the nanoparticles are heated irregularly, randomly, by water molecules, and so they don't proceed in straight lines. They are this irregular, broken trajectory. It's very famous. This is the Brownian motion. This is random motion. Unfortunately, there are very established ways to treat this Brownian motion in implicit solvent. This Langevin molecular dynamics, which is the same as molecular dynamics. So we have the equation for the position and the momentum. There's a missing line. This is the force field. And then we have 2 terms more. The first one is the drift, which is due to the viscosity, and we can link this gamma parameter, which is the inverse of time, to through the Stokes-Einstein equation, to the viscosity of the fluid, the mass of the magnetic nanoparticles, and the radius of the magnetic nanoparticles. Of course, we need to know all these quantities. And then there is the diffusion or random forces, and this is a stochastic process, as I told you yesterday. The average of the stochastic processes, the stochastic variable, is 0, and the correlation between these 2 fields at 2 different times is a delta function. So it's white noise, as is referred to, and depends to the coefficient gamma of the drift through the temperature. So no temperature means no random fluctuations of the force. Also, no friction means no random fluctuation. So in this way, we can treat the random motion of the magnetic nanoparticles. We still have to provide a potential, since we want to focus on the effect on dipole-dipole interaction. We selected the simplest, or one of the most used of the simplest potential, which is the Weeks-Chandler-Henderson potential. Is just a Lennard-Jones potential, which is truncated at the minimum. So this blue line. So this is a soft sphere potential. The nanoparticles will avoid each other, but there is no other source of interaction between them. This is an approximation, of course. This is for the, let me say, translational motion of the magnetic nanoparticles. What about the magnetic interaction? We know that will be a dipole-dipole interaction between tiny magnets. So how is this treated? But first of all, we have several magnetic nanoparticles in solution. This is the concentration I was referring before. We know what is the dipole-dipole interaction. So it's missing a ratio here. And as I said, as we use the most simple soft sphere repulsion, so the only long-range interaction is the dipole-dipole interaction in this case, just to simplify the analysis of our results. And in these calculations, because tiny, small vial, we have neglected all the hydrodynamic interaction. So what about the magnetic part? So we have certainly, if we have this alternating external magnetic field, this radio frequency. Since there is this dipole-dipole interaction, there is also a magnetic field which is then generated by the dipole-dipole interaction there. And then we want to use similar formalism, actually we have to, just to be coherent. The similar formula is to the one used for the random Brownian motion. So we will add a stochastic fluctuations, a thermal fluctuation of the field. This is equivalent of saying that there will be random Brownian rotation of the spheres. Let's focus to each of these components one by one. First of all, dipole-dipole interaction. This is an interesting interaction, again, drawing from the previous analogy. So each nanoparticle is a tiny magnet. The dipole-dipole interaction is anisotropic, so the energy depends on the angle and the orientation between, and the distance, of course, between the nanoparticles, and it favors alignment of nanoparticles. Of course, this will not be in solution with thermal random motion a perfect alignment, but this kind of configuration minimize or try to minimize the magnetic internal energy. Then the external field. So I have an alternating external field. Let's say I have an external field and this is fixed. If I have a single domain nanoparticle, I can simplify the description. This is a tiny magnets in solution. Let's say, let's simplify first and then add the complication. If the viscosity is 0 or this magnet is in vacuum, we have a very clear, and probably we all know, clear equation for the motion. This is Larmor equation. So it depends on the cross product between the external field and the magnetization density of the nanoparticles through the gyromagnetic ratio. And the solution of this is precession, and this is the so-called Larmor precession. The frequency of this precession can be high and is proportional to the modulus, to the magnetization of external magnetic field. This is a very simple motion. The magnitude of the magnetization vector does not change, just proceed. But it will do that forever. So without any mean of dissipation, without friction, viscosity, that will keep rotating about the axis. But we know that in order to minimize the energy, the external magnetic field and the magnetization should align. So there is a missing term in our equation of motion, and this term accounts for the dissipation and has been derived in different forms by different physicists, and this equation comes under the name of Landau-Lifshitz-Gilbert equation. We have the same terms that you saw before, accounted for the free precession, and then a new term which depends, thankfully, on the viscosity and then on the time derivative of magnetization. So it's not as good as an equation of motion because it's still implicit. We have the time derivative here and there. So it's much better to write down this Landau-Lifshitz-Gilbert equation in an explicit form. Just to simplify the notation, I will use alpha to indicate this dimensional damping constant. This is 0 in vacuum. And after a little bit of algebra, we can prove that the original formulation of the Landau-Lifshitz-Gilbert equation is exactly equivalent to this explicit form. You see that now in the explicit form we just have the time derivative on the left. But there are important consequences due to this explicit form. Now the gyromagnetic ratio is not the original one, which just depends on the ratio between the electronic charge and the electronic mass. There is a correction due to the friction. Sort of makes sense. In viscous fluids, the precession slows down, if you want. And then if we compound everything in this round parentheses in a sort of effective field, which depends on the external fields, but also on this, let me say, drift field, if you want. Our Landau-Lifshitz-Gilbert equations looks like the original Larmor equation. And this is a nice property of this spin dynamics, because we can use exactly the same good integrators that we can use for free rotation. We just have to take care of the redefinition of the magnetic field at each time step. And this is exactly what we do. If you've been following up to this point, I cover, let me say, the deterministic part of a motion. I still didn't cover the stochastic part. So it means that since I introduce frictions, the system will try to minimize the magnetic energy. And you are really sitting at the minimum of the of potential energy, magnetic energy, in this case, at 0 temperature. But it's, well, this is not the range of temperature that we want to target. We want to target room temperature, slightly above room temperature. So we need to introduce also thermal fluctuation. So there will be a distribution of magnetization, not just a value which minimize the magnetic energy. In order to introduce thermal effects, we have to introduce thermal fluctuation in the same fashion as for the Langevin equations. And so there will be a stochastic term, already mentioned, adds to the deterministic term. And that has been pioneered by Brown, not the Brown or Brownian motion, of course, some century after. So again, more explicitly, how are the correlations and the averages for this stochastic process, which gives the fluctuating thermal magnetic field? Is the 0 average. There is no net effect. And then the fluctuation are still white noise, delta correlated, and they depend again on through alpha, through the viscosity, the temperature, and then also the volume of a nanoparticle. If you have a large nanoparticle, you can imagine you won't see these fluctuations. And this is why we have the volume there. Am I going with the time? Okay. So now I skip all the details also because I provide some of these details during the school, but of course having an equation, it doesn't mean that we have a solution of the equation. These kinds of equations, very seldom they can be solved exactly. Our strategy is to implement them. We have a code, actually we are about to release our code. The stochastic Landau-Lifshitz-Gilbert equation you cannot find in, let me say, the most common molecular dynamics codes like LAMS. This is why we implemented that in a separate piece of code, and perhaps in the future we'll implement in a major piece of code. So assuming that we have this mean of solution, numerical mean of solutions, what we want to study? We want to study this so-called the magnetic susceptibility of our magnetic colloids. The magnetic susceptibility chi, the volume susceptibility, is defined this way. It's the response function of the magnetization after you apply a magnetic field. Turns out that can do several things, but there is an important component, at least in our case, which is an exponentially decay component, a long time, with a characteristic decay time. In fact, there is even an exact solution for this system. Is exact, unfortunately, just for single magnetic nanoparticles. So we need to verify whether or not it applies to many magnetic nanoparticles. And this exact solution is the equivalent of the Bi theory of relaxation. And this, if you haven't seen this form, is exactly the same as the Bi model. Terms, of course, change slightly. What is the Bi relaxation time? Here is called the Brownian relaxation time. Again, it depends on the volume of the nanoparticle, the viscosity, so this is 0 for 0 viscosity, and the temperature. And then if you have some acquaintance with magnetization, this is nothing else than the static Langevin susceptibility. So it's very useful to have an exact solution, although it applies to a single nanoparticle, because we can first validate and also look for the deviation. And we can imagine if this is valid for one single nanoparticle. If we have a very diluted colloidal solution, we can expect that that should be a very good approximation. And we'll see this in 1 second. Just to provide a little bit of graphical explanation of this form, the Bi susceptibility, I used, let me say, experimental values. So radius about 75 nanometers, so this is a large nanoparticles. Temperature is room temperature. Viscosity, we usually have two cases, water and blood. And here is the angular frequency. With respect to the frequency inerts, you have to multiply the frequency inerts to 2 pi. So this is probably frequency of kilohertz, probably slower. Well, you can look at this functional form. This is just the imaginary part, which is the part of the susceptibility related to the absorption. There is a peak. The peak is located at the frequency which is equal to 1 over tau b, the Brownian relaxation time. And clearly the position of peak depends on the viscosity. In our experiments, I think the equivalent frequency is here. So we are much, we're not at all close to the peak. So if I have to apply this to my experiment, I would probably interest in the tail, not in the peak susceptibility, not in the resonance. How does the SAR, which is a quantity which with certain uncertainty we can measure in experiments, how is the SAR related to the susceptibility? Well, for small field, this is done through the fluctuation dissipation theorem. So the power absorption for a given amplitude of field, H naught, and a given frequency, angular frequency, is given by 1/2 the frequency, the imaginary part of a susceptibility, this one, and then the square of the amplitude. As I said before, the frequency here is 2 pi times the radio frequency that I provide in kilohertz. This is the imaginary part with this 2 prime, and this is the square of the magnetic amplitude. If I substitute this form in the exact the Bi expression, the SAR provides it's not as specific as a function of the volume, it's specific as a function of the grams, either the grams of nanoparticles, more often the grams of manganese. So we need to divide this expression by the density of the magnetic nanoparticles. Okay, there is no problem in working out the calculation at this stage. This is the solution, depends mostly on the Brown relaxation time, and this is the plot. And you can see there is a nice saturation with the frequency. And this is true because we have the frequency square at both denominator and numerator. So and by the way, our value here is not very far from what is measured in experiments. This is just an interesting result. It's difficult to claim we are spot on. There are too many variables, but it's not miles away to the initial slope. It's the initial slope in the experiment is 1955. This is in excess of 2000. And we say operate in the limit of large frequencies. So this is independent of the frequency. If I substitute the numbers for the Brownian relaxation time, you see that we have an expression which is in fact independent of both frequency, temperature, and volume. I want to stress this is true if we neglect nail relaxation. 5 minutes, wow. Nail relaxation, so for very small nanoparticles. So let me go quickly to the simulation of small nanoparticles in water. We don't have an exact results, but we can compute the so-called magnetization, magnetic autocorrelation function from the simulations, from the spin dynamic simulations. We also expect this to decay exponentially. We can relate the exponential decay to the Brownian relaxation time, which in the case of single particle, I want to remind the expression. Those are the results for small, this time magnetic nanoparticles in solution. We use simulation boxes of different size. This is not important, just to say that by increasing the concentration, there is a clear deviation from the expected Dipole single particle model to the results at very high concentration. This box 5 means that it's almost all coagulated. At low concentrations, there is almost no difference between the the single particle results. So the effect of aggregation, the effect of many body interaction is not very high. But if we increase the density, increase the concentration, we have strong deviation. We can still describe this as decaying exponential. What about, okay, from this we can obtain the imaginary part of a susceptibility, which is decreasing with the concentration. So this suggests that the higher the concentration, the lower is the SAR. Is that true? Yes. For the small nanoparticles, this from molecular spin dynamics calculations, the effects of the concentration is to decrease the SAR. And to some extent, we can still use the Brownian expression or the Dipole expression for the susceptibility. We just have to use effective friction. The effect of the aggregation, in this case of the concentration, is to increase the friction, which makes sense. There is stronger interaction between the nanoparticles and then they relax more slowly. A little movie to finish up. This is for the simulation of the larger nanoparticles. And you can see they clearly tend to form short chains. Here there was an event, perhaps. So we use in periodic boundary conditions. So if you see some magnetic nanoparticle disappearing, it will appear on the other side of the box. And okay, here we have a longer chain. Here there was an event. In 1 second, we'll focus on, this is what happened. So the red arrows, they indicate the average force. They are all aligned, so these three magnetic nanoparticles, they behave like a single rigid bodies. You perhaps cannot see, but there is a very fast rotating arrow. This is the magnetization. The fast rotation is the Larmor rotation. And towards the end of the simulation, you see that there are quite a few chains. And here is another event. Those are very long simulations. This is why we had to use so far just a few nanoparticles. Those are 55 nanoparticles. But the concentration is the experimental concentration. Now, last two slides, promise. So what is the effect of the formation of chain? Now, again, I can compute my magnetic susceptibility from the experiment, magnetic autocorrelation function. From the autocorrelation function, the magnetic susceptibility. I can fit the data. I find what is the characteristic time, let me say the effective Brownian time. If I plug the effective Brownian time in this formula, here I see that the effects of having chains of nanoparticles in water is still, it's almost the same having blood. So it means that, again, having larger objects formed by small nanoparticle, it is the effect, the average effect is to have like higher density. They rotate more difficultly. To finish up, what is the effect on the SAR? The effect on the SAR, of course, is to reduce the SAR. If there are dischaining solutions, the SAR is much reduced and is approaching the value of the value of blood, which means that probably the effective viscosity that one can use to describe this fluid is very close to the viscosity of blood, which is roughly 3 times the viscosity of water. So we use the single exact theory, the exact theory, for single nanoparticles, but we applied the Brownian time obtained from the simulations. Conclusions. Sorry for the long talk. So from the experimental part, microwaves improve the crystallinity and enhance the magnetic properties. In fact, they are very close to the ideal value. Simple model, the Brownian models, we don't have nail relaxation, is in this case very close to the initial part of the heating curve, the initial heating. I don't want to say that this is an explanation, because there are too many things that we don't have under perfect control, including experimental values. But it's encouraging in the sense that this theory can be used, must be adjusted perhaps for the aggregation. And in fact, from molecular dynamics or spin dynamics calculation, we see that the aggregation of magnetic nanoparticles can be described to a certain extent as an effective friction, effective viscosity. Those are the good points. The bad point is that our nanoparticles are still too large. We are happy that they are very good crystallinity, but we want still to decrease the size so that we can also test the nail relaxation. Our code can deal with the nail relaxation, but the particles are still too large. There are experimental uncertainties about the quantity measured. In particular, there is no agreement about, let me say, the experiment, the protocol to measure the SAR from the experimental curves, especially in the case when you have non-uniform SAR, or if there is a phase transitions. And the agreement between the modeling and the experiment can be improved. So from the simulation, it seems that we can rule out the presence of chains, because they decrease too much the SAR. It's not the value observed. I think it's too early to conclude this. There are indications that there are not this chain of nanoparticles. What we would like to add in order to check with higher accuracy is a better modeling of the magnetic, the colloidal interaction between the magnetic nanoparticles, in particular this DLVO potential. And with this, I conclude and I thank you for your attention.
Okay, question?
Thanks. Because this is a physical medical school, I would like to ask about the perovskite applications. If you could think about the heat synchronization in magnetic resonance, do you think it has some application to reduce it? Because the machine, of resonance and magnetic, tends to elevate the temperature when it is functioning.
Which machine?
The resonance magnetic.
Oh, the big one. Oh yeah, okay, I understand.
Synchronization in a certain moment, and this increase the temperature. So if you are thinking, if you're thinking some applications could be possible to the perovskite to have
as a contrast medium or better.
Because I suppose you introduce it in the body. It's like a science fiction, this is, no? But you introduce it in the body, and it will have interaction with the resonance of the machine.
Yeah.
So.
Okay, thank you. That's a very interesting question. And I probably was not clear about this. There have been trials. What they would like to use, and I think there are prototypes. They are not, let me say, human-sized coil. There are small coils, and what they use is, let me say, the stray field from the coil, which of course it means that this device must be close enough, and it will have, okay, the magnetic field should not be too high, because otherwise it will induce eddy current in the body, which is never good. So about, and I think there will be also possibly something in vivo. If I understand correctly, the big gap between, let me say, the study we done and the application is let me say, the third challenge. Okay, I don't want to scroll everything. There was a list of challenges. Third challenge is the description of the environment. Now, what is believed is, although these nanoparticles are relatively free to rotate in blood, they get stuck when they enter in the cellular environment or between cells. So it means that this Brownian rotation mechanism will be highly hindered, probably absent. So this is why they want, it's yet another reason to want small nanoparticles. Because in that case, the coherent rotations, so the hysteresis losses, they will produce the heating mechanism. And even if they are immobilized, because this is the internal coherent motion of the magnetization. Sorry. There are other possible applications. We don't do this yet at Queen's University, but there was some thinking, thought showers, as I said, to use these nanoparticles to deliver drugs, for instance, because if you, it's not my field, so I report what I heard. So if you can functionalize these nanoparticles in order to have some drugs, some active molecules, then the active part can be released upon heating of the nanoparticles. Again, I guess the challenge here is to have something stable. And this is the chemical part of this, and also to target the part of the body that you want to target, which is highly non-trivial, I think.
You mean it's like in Spanish we say vehículo excipiente, the soft shower?
Apparently brainstorming we cannot say anymore. Yeah. Is it okay? The answer? Okay. Thank you.
Other question?
About the challenges you mentioned,
Okay, I'll
you
go
mentioned protein corona. Could you tell us a little more about this? And if you know,
I would like to.
you know how this could affect the physical properties of the
Again,
nanoparticles?
it's not my field. I suspect you know about this much more than I do, but I'll tell you what I know, and then we see if we agree. Most of the literature is about ferrite nanoparticles, so magnetites. What happened is in the I think in the blood, the small molecules or even sugars, they get attached, and they signal here there is something foreign to the body. So let's do something. There are ways to functionalize the surface of the magnetic nanoparticles, in fact any nanoparticles, to decrease this response. In fact, this increased response, this protein corona can have two effects. The first one is to enhance the coagulations. So these nanoparticles, they get this protein corona, they get stuck, and then they are eliminated the usual way. The other action, the other problem is that they are so big that they might move, but they never reach where you want them to go because they are too big. In fact, there are 3 points, because if they are so immobilized, the SAR might decrease at the end. So there's a lot of chemistry, and I'm afraid I'm a physicist here. So, but I know that they want to functionalize the surface of the nanoparticles in order to decrease or get rid completely of this immunoresponse, I think it's called. Is that okay? It was good.
More questions? Okay, if there is no more question, we will thanks again to Dr. Lorenzo Stella.
Thank you.
So we can go there for the